It was in early February 2025, and there are some really interesting things happening politically. And I think that it was very easy as a scientist at that point to feel lost or undervalued. And so I just thought like, oh, this would be a really great way for like us to do something to point out what we're doing and why it's important and why we should continue to fund this sort of science.
Geology is a field that many people associate with just licking rocks or just getting oil out of the ground. But there are so many subfields of geology. Geology is the study of Earth. And fields like volcanology, the study of volcanoes, lava, magma, and all the associated geological processes. Or petrology, the study of rocks, their composition, texture, formation. Or my previous field, geochemistry, which essentially looks at the chemistry of rocks to figure out the conditions under which they form, which can give us all sorts of information depending on the context. We can use geochemistry to reconstruct Earth's ancient climate millions of years ago, or we can use it to help find mineral resources in Earth's crust today. There are endless applications of these fields of geology. But how are these fields important to society? How does the research that's currently being conducted within these disciplines affect our day-to-day lives? Well, today I got to speak with not one, but 3 experts who are co-hosting a research session at the Geological Society of America's GSA Connects 2025 meeting this October on this exact topic. So I spoke with them today to talk a little bit about this session, but mainly to answer these questions about why these fields of geology are so important and how heavily they impact society. And dare I say, this is actually one of my favorite interviews to date. I did not expect going into this conversation that it would get so deep, so impactful, so wide-reaching, but it really did. So I won't give anything away. Let's jump right into the conversation.
My name is Michelle Gevedon. I'm an assistant professor at Colorado College. I am a high temperature stable isotope geochemist and an igneous/metamorphic petrologist. And my main interests in research are finding fluids in the crust, following them around and finding out what they're doing, the way they transport elements, where they came from, the way they change the behavior of the crust. And so it's sort of my realm of high temperature geochemistry.
Hi, I'm Nikki Seymour. I'm an assistant professor at Occidental College in Los Angeles, and I am somebody who studies kind of the intersection of structural geology and tectonics with petrology. So I'm really interested in the way that rocks deform. What does that mean for how the plates move around? And then how does mass and chemicals move through the earth during that process? I also think it's really exciting that some of these processes will produce economic deposits, which are going to be very necessary for us as we continue to increase our energy demands.
And I'm Tyler Grambling. I am going into an assistant professor position at Denison University, and I've been at Colorado College as a visiting professor with Michelle. I am also a structural geologist. I focus on fault fluid interactions and kind of thinking about deformation as a geochemically driven process, and a lot about the intersection of fault dynamics and subsurface hydrology, so how fluids are moving around in fractures and reacting with rock and driving mass movement, that type of stuff.
Wow, very interdisciplinary areas. You know, having been a student in structural geology, I wouldn't have necessarily stuck that with like geochemistry and fluids and things. So that sounds super cool. So we'll start with what motivated you guys to put together this session that you'll be running at GSA Connects this year, the importance of petrology, volcanology, and geochemistry to the issues of societal relevance session. This sounds super, super interesting. We're always wanting to hear more about how are the things we do in geoscience relevant to society. So what, motivated this?
So last year at GSA, we had one of our metamorphic petrology sessions, and somebody asked the question, why are younger students, new students, not choosing to study higher temperature petrology or geochemistry as their discipline? Of course, we didn't really land on a firm answer, but it was sort of implied and suggested that perhaps it's because a lot of people now are making decisions, as they should be, with environmental justice in mind and with the environment in mind and sustainability. And perhaps the connections between high temperature geochemistry and petrology are not as obvious as in other disciplines, like where you're directly studying modern climate change. And I was just sitting in that session and I thought to myself, well, like the people in this room are the people who can answer that question, like what is so important about petrology and why should we be focused on studying geochemistry and volcanology, basically the myriad ways that we study the inside of the earth. And I had this idea like, oh, we should do this next year. We should just have this whole session where we all get together and talk about ways in which what we do is important to society and sort of like celebrate what we ultimately do and why it matters. And then when the calls came out for having sessions, it was in early February 2025, and there are some really interesting things happening politically. And I think that it was very easy as a scientist at that point to feel sort of like lost or undervalued. And so I just thought like, oh, this would be a really great way for like us to do something to point out not only to ourselves, but to our peers and to like new scientists and to the public what we're doing and why it's important and why we should continue to fund this sort of science. So that's sort of like what we're hoping that this session winds up being, just an example that students can come to, or people who are like trying to decide what subdiscipline of geology that they would like to pursue further. Just come and find out what it's all about and all of the myriad reasons that it's incredibly important, especially right now, that we study the interior of the earth and geochemistry going forward and the impact that these disciplines can make.
Yeah, it really speaks to me what you said about, being a scientist in February 2025, feeling very undervalued. It just is really inspiring that you saw that and you were like, well, let's show people why we matter, what we're doing, and why it's so relevant to society, because it so is.
It so is.
And yeah. And I mean, even as students in these fields and departments, I was just saying before we got started, as I took petrology as an undergrad, nobody was talking about how this stuff that we were learning was relevant to society, not, in depth at least. And so I'm just really glad that you'll be able to put this together, and we'll hopefully share it to some members of the public here, but also to students at the meeting. And so getting right into it, what is the importance of petrology, volcanology, and geochemistry to everyday life?
If we want to go forward with this idea of moving towards more sustainable energy dynamics, solar, wind, and then ultimately battery capacity and storage, we need to increase the capacity of resource extraction across the world. And there's kind of two ways you can do that. You can do it purely by a profit and kind of greenwashing standpoint, right? Go in and take as much mass, as much stuff as you can, as quickly as you can, build the batteries, and it looks really good. Or you can go in with understanding the petrologic and the geochemical processes, both forming these deposits that should be mined and requiring us to extract the rare earth elements and the heavy metals of interest, and use that knowledge to minimize the environmental impact of our progress towards more sustainable energy.
I think it's very emblematic of students right now, where they have this environmental ethos, right? Where like everything green energy is good and everything that's extractive is bad. And that's not to say that I love mining or anything, right? Or don't see that mining is problematic, but there exists this disconnect in people's brains, right? Because we're super removed from where the materials that make the things that we use in every day of our life, right? If your cell phone, right, has copper in it, your solar panels, your lithium battery in your phone or in your car, we're very removed from where these materials come from. So if we want to have this green energy transition, it inherently means an increase on critical mineral demand. And that inherently means that we have to proceed forward with mining practices. And that's such a dichotomy, right, for people to think about, that I think like this is one of the really important reasons that we talk about where you find certain elements and what processes move elements around and how you concentrate elements in a certain place and how you find those elements. Much of that happens on the interior of the earth. It's not something that we can often observe directly. And so even if you're not directly studying economic geology, if you're not directly looking at economic deposits or extractive practices or looking at ore formation, everything that we're doing is somehow related to mineral resources. And if it's not related to mineral resources, it's related to resource security or climate change or to disaster resilience.
Absolutely. That disconnect is so huge. And Nikki, I want to hear your opinions too, but really quick before we get to that, so you mentioned critical minerals and how the push toward green energy is inherently increasing the need for us to mine more critical minerals. Can you just define what are critical minerals and why are they connected to the green energy transition?
Yeah, the Energy Act of 2020 defines critical minerals as those that are essential to the economic or national security of the United States. So critical minerals don't necessarily include fuel minerals or water or ice or snow, and they don't necessarily include things like gravel or sand or stone or pumice or clay. All of those are non-renewable resources that we use all of the time, but specifically critical minerals are those in which we use to have like either manufacturing or the production of energy. So for example, lithium is very important to the rechargeable batteries that we're using currently, the modern technology for rechargeable batteries. Rare earth elements are incredibly important in all sorts of electronics and also in magnets that make wind turbines go. So we're thinking beyond what we would typically consider like an earth resource, but it's also beyond what we've thought about traditionally, right? Gold, silver, copper, that sort of thing. So expanding that definition of what we need. Cobalt is a really big one.
The one other one that hasn't been mentioned is kind of the idea of gold hydrogen, which gets into all the industry terms, but it's basically thinking about how hydrogen can be used as an alternative fuel source without net positive carbon contributions to the atmosphere. And a lot of the geologic work that's focusing on that is both hydrothermal systems and retired oil wells and things like that.
Yeah, I did just want to add to the conversation, especially about, this idea that geology has contributed to our current state, which is true, right? Like the reason we were able to have the Industrial Revolution is that we figured out geologic mapping and we could predictably locate where resources were. And throughout the theme, I think it's important to highlight that as we learned more, we switched to more efficient sources of fuel. And we're at this nexus again, right? So we were focused on coal. There are obviously drawbacks to coal. As those were recognized, we switched to a more efficient fuel, right? So that became hydrocarbons. So we're now in this next transition. So for every switch we make, there's large gains to be had. You switch from muscle power to steam power, right? That changed the way society operated. And I think one thing that's really important is, yes, geology got us here, but we've also been making improvements and we have the opportunity, if we can focus these studies, determine in advance what are the drawbacks, how do we effectively manage them so that in another 50 years, we're not having this conversation about the extractive practices, right? So as we learn better, we do better, but that means we need people to be contributing to the conversation so that we can make these advances to better understand these systems. The other societal impact is that resources are not uniformly distributed, right? Like rare earth elements, it's not like we can walk around in Texas and necessarily find a rare earth element deposit. So where are they located? Why are they located in those places? Because this has huge implications for how our economic systems work, how our geopolitical systems work. And so these studies are necessary to say, like, I work in iron oxide copper gold deposits, and these are also a potential resource for rare earth elements. And so right now there's a few key places where we can get rare earths, but if we can open up through petrologic study this new domain, we can expand where we can get these resources from in terms of, physical location on the earth, and also just expand our supply.
There's also huge implications for social justice here as well, because like Nikki said, the distribution of critical minerals is not even. And so when we think about ways that we might be able to target certain deposits or maybe use them, right, there's also opportunity for exploitation of countries like with lower environmental standards or socioeconomic standards. And just because it's in a different country, we shouldn't exploit people like that. And so making sure that we are conscious of all of the aspects of it, I think are incredibly, incredibly important.
This is already such a really wide-reaching conversation. I didn't expect it to be, but everything you said now makes so much sense. Essentially, we've got that we need these fields to find and extract these critical minerals, which we need for the energy transition, which we need to address and mitigate climate change, which we need these fields to find where these are, to map where these are, to understand how to extract them, all these things. And we also need to be conscious of the fact of they may lie in some areas that have societal or more directly, implications toward people and communities. All of these things are incredibly relevant. And so actually my next, couple questions were kind of like, what are some ways that these fields are relevant to resource security, climate change? We've kind of hit these things already, but what about natural hazards and or other impacts of climate change that these fields might be helpful to address?
Right. There's obviously so much more than just critical minerals to why we need to make sure that people are still interested in studying petrology. Like if we even just look at the subdiscipline of volcanology, that's one that people feel like a really tangible connection to. It's one of the few instances where we can watch our geology happening, right? And nobody wants to be standing in the path of a volcano, right? And so it's that's really obvious. And so the hazard mitigation component of volcanism is a very obvious one, but it's more than just eruptions, right? There are more hazards that go along with petrology, even with volcanoes on their own. But we can also look at the connection between subduction zones, which are amazing petrologic factories, right? But they also create these megathrust earthquakes, and the seismic potential there is incredible and it's dangerous. And we have really large populations who live in really seismically active locations above subduction zones, not just in our country, but in other places. And it turns out that the the exhumed rock record, holds information about the way that seismicity is expressed, how often these subduction zone earthquakes occur. There's also conversations to be had about the deep carbon sequestration potential of petrology, right? So like the way geology and deep time fit into the global carbon cycle, right? So when a lot of people learn the carbon cycle, they learn about what's happening up at the surface or in the critical zone. And it turns out, right, that we can sequester carbon deep in the earth. There's lots of petrologic processes that can pull CO2 out of the atmosphere and store it for potentially really long times. And so it just proliferates beyond critical minerals.
So one of the things that Michelle just brought up, I think there's twofold. One, the entire subdiscipline of volcanology. Some of the questions that I get is, why do people continue to live near volcanoes if they know that they're going to erupt? And so the entire field can study, well, is this volcano still active? How frequently does it erupt? Why do we continue to live these places? Because they're fertile grounds, right? So the geochemistry of the volcano makes it possible to grow all kinds of crops which have sustained societies for a really, really long time. So there's both this gift and this hazard. And how do you balance those two things? It's by understanding the system, right? How did the system get here? And then the follow-up to what Michelle was just saying about carbon sequestration, right? The reality is that the Earth will correct our current CO2 levels. The trouble is it's not going to do it on a timescale that we are likely going to coexist with. But if we can understand how is the Earth going to do that, right? How is it going to lock that CO2 into minerals to transfer it into the geologic realm? Are there ways that we can replicate this process, right? How do we, on human timescales, replicate what the Earth is going to do geochemically? And then we may be able to shorten that timescale into something that's going to better align with our lifespans.
I love it. Really quick, I'm sure, Tyler, you have something to add, but really quick, I love that you mentioned that because climate change mitigation and carbon sequestration, this comes back to the disconnect we were talking about earlier. Students that are going into, undergrad and they're choosing their major, they're not thinking that they could do those things by majoring in geology and studying petrology, but they can, because where would you sequester the carbon? Into rock? This is the thing we need to understand. And that's that disconnect is we can study climate change. We can sequester carbon by understanding rock, by understanding geology, by understanding petrology. And, the things that we live on, the things that we want to sequester the carbon into. So that's just such an important and seemingly simple connection that just isn't made. And like just pointing that out is like, oh, I never thought about that. But you're right. People tend to focus on the more surface level, like critical zone, like soils, plants. We can go deeper than that. We can go to the rock. And that's, we need geologists for that.
A kind of side tangent on like relating natural hazards to all of this is that so I work a lot in an area of Peru that's really heavily glaciated, and it's tropical to subtropical, so it's under immense climate threat right now. And so there's like 2 or 3 of us that are interested in doing like hard rock geology there, and everyone else is studying glacials. But I was looking through literature last night and saw a really interesting line about the idea of glacial outburst floods, which is that basically you have either glacial mass fall into a subglacial lake, or the glacier itself converts into like an ice fall event and endangers populations. And the Cordillera Blanca, where I work in Peru, is a really interesting example of that, because people have been evoking it as this thing that's driven by earthquakes because of this range. But 6 of the 12 recorded instances of this being triggered, the glacial outburst floods being triggered by earthquakes, were a single event driven by a megathrust earthquake in Peru. And now we're actually able to look at these things and say, okay, so this is a relationship that can be thought through in subduction zone processes, but now we can use that as an analog to look at what's going to happen as we are naturally retreating these glaciers and destabilizing these ice masses. And then the kind of flip side of that is, because of the location of this area in an area with a lot of copper sulfide deposits and actually one of the larger gold deposits in the Americas, we're seeing a lot of what we would consider to be acid mine drainage occurring just by the weathering of the bedrock. So through better understanding the processes that form those elements and bring them up to the near surface, we can start to think about how we can minimize the impact of these really kind of toxic substances making their way into waterways, both through kind of mechanisms that are a little bit more natural and where we have already mined and created a lot of this nasty stuff that then has to be dealt with.
Wow, I never thought of everybody thinks of ice melting as like, okay, that's going to cause sea level to rise, but you don't think of the other side effects that pretty much any geological process has, but it's so wide reaching. And actually, my next question, and so Tyler, you kind of did this, but maybe Michelle and Nikki, you can also, but my next question was, can you share an example of how your research specifically has impacted society?
I had an undergrad who looked at the copper assays from a mine in Utah and the stable isotope compositions of calcite that was in coeval veins, so veins that formed at the same time as the copper. And we found really distinct stable isotope compositions of those calcites that tie the creation or the enrichment of the copper in the system to a very specific place in the skarn and to a very specific process. And so we're hoping that that mining company who's actively mining there now is going to be able to use some of his data to inform their mining decisions, to begin with the end in mind, and be less destructive and more productive in their process.
That's really cool. I never would have thought of that. And I did some stable isotope research myself as an undergrad, and it was always for like very, very ancient earth, reconstructions, never for today things. So that's really interesting. I never thought of that application. Nikki, do you have one?
So I have a couple of different ways that I look at the earth. Down in northern Chile, I'm really interested in the link between deformation, so how do faults form and how do they translate pieces of the crust along the margin, and how the behavior of those faults and that deformation is related to emplacement of arc plutons. So as magma bodies are intruded, they are bringing in a lot of heat to the system, and you may take something that would break in a brittle fashion, and when you start to increase the heat, instead you'll transition to something that is going to flow, even at relatively shallow levels. And then once you break something in, if you have the transition from flow to fracture, which generally will happen in the shallow crust, as Michelle says, like there are fluids that come off of these arc plutons and they rise along these cracks, and they can transport fluids, they can transport metals, they can transport a number of things. And so in northern Chile, we have this really interesting connection of a long-lived fault system. There was a long-lived arc system, and then co-located with both of those things are significant economic resources, which are critical to the economy of Chile. And so trying to understand the relationship between those things which are actively contributing to the lives of Chileans and then to everyone who is benefiting from those products.
Wow, that is so wild. All of those are so like never would have thought, that those things connect in that way. Like all of those fields and community impacts. And oh my gosh, that is just so crazy.
I mean, so none of us have talked about planetary science, which is another branch. And so why is this relevant? Well, there's a lot of companies which are interested in going out to space and like finding habitable homes for humans. And like, hey, if we're not going to be able to find natural resources on Earth, maybe we can find them in asteroids, right? Maybe we can find them in other bodies. Petrology, the petrology branch that is planetary science, that is how you do that. So if we want to study these extraterrestrial bodies, both through remote sensing lens, once we are starting to get samples physically returned, petrologists are going to be the people that are deeply involved in understanding what some of these other bodies are made out of. How possible would it be do you want to terraform something? Do you have the requisite geochemistry for that to make sense?
Yeah, no, that's such a great point. That's another disconnect I think people have is like, why would geologists and petrologists and geochemists need to be involved in like planetary missions or planetary science? It's like those things out there, they're floating rocks. Those are rocks. And like we have to understand that. So people don't think about that. They just think about like, I guess, engineers and biologists if there's life there, but we need to look for evidence of life and or habitability and or mining potential in the rocks.
Or even just the way that other planets have changed in the past, right? Like we live on a really dynamic planet. Part of that dynamicism is why we're able to live here. It's my favorite planet, Earth, by the way. Everybody, everyone's like, pick a favorite planet, and they pick something else. I'm like, Earth, I love Earth. But, like we look at our close neighboring planets, and those planets have also been dynamic more so in the past. And if we can understand changes that those planets went through, then we can better understand the changes that are possible for our planet to go through as well, especially at this time where we're very concerned about accelerated rates of change.
Getting back to kind of conversation around natural hazards, how can petrologists and geochemists contribute to kind of community resilience in hazard-prone areas? Like, can this research contribute to warning systems and public policy?
I think warning systems are an interesting approach there, specifically with respect to volcanic hazards. There isn't really a meaningful way to have a true predictive system for earthquakes. But with volcanoes, you get a really interesting sequence of both seismic cycling and geochemical cycling. So kind of this whole conversation about petrology, geochemistry, and tectonics, where you can monitor things like the resistivity and salinity of groundwater in a volcanically active area. And preceding an eruption, you're going to start to get injections of all of these fluids that Michelle and Nikki were talking about that come off of these magma bodies into the local groundwater. And so you'll start to get these gradual increases in the electrical resistance and the salinity, and then suddenly that'll drop off. And that's kind of your warning sign that you're about to have a fairly large-scale eruption because you're actually draining the groundwater into the space that had just been occupied by magma. So we can get these really kind of fascinating tie-ins with direct monitoring systems, and then we can go back and look at historically large eruptions and see what the rock record is telling us about that, to see if we can tease out a little bit more about maybe either deeper processes or something we just hadn't noticed before that might give us another couple days of warning in those instances.
So I think another thing to think about is Nikki brought up earlier, like why people continue to live in and near volcanoes, right? This idea of volcanoes making really fertile soil is important, but also people have really strong cultural connections to places that are volcanically prone. And so I think there's really good examples of ways that communication with societies can be effective in terms of warning systems and actual hazards in ways that can actually save people's life. And we are just becoming more informed about the way that hazards happen, about volcanic patterns, about styles and different versions of volcanic hazards all the time. And I think really having a connection between communities and societies who live in these volcanically prone and active areas with scientists is only going to continue to benefit those societies.
Two things I love that you point out. One, the connection that communities have to these areas. And, just instead of trying to get people away from volcanoes, like let's just protect them. Let's, work on studying these things, creating warning systems, whatever it may be. But also the argument, oh, why do people live near these volcanic regions? We could say that about all of California. It's earthquake. We can't do away with the hazards. So let's study them. Let's understand them. Let's try our hard. Well, it's hard to predict earthquakes, but let's try our hardest to predict these things and at least understand how to respond and how to build more resilience, in the communities when these things do happen. But the second thing that I really love is both of you mentioned looking to the past to, study the patterns and to better understand our modern volcanic hazards. But this can apply to a lot of different climate change. For example, my, research as a graduate student was in geochemistry and kind of reconstructing past ocean chemistry and climate. And I always talk about on my channel how important that is to understanding modern changes in ocean chemistry and changes in climate and how that might progress.
I was going to say the other thing that we can study through high temperature geochemistry and through petrology in all of its many forms is the rate at which some of these things are occurring. When I was an undergraduate, I had this idea that, mountain building and everything in the earth took tens of millions of years. And as we've learned more, developed better techniques, we're increasingly realizing that window is much, much shorter. Things are happening on much faster timescales. We're not really building a mountain over 30 million years, or maybe you are, but actually what you're doing is you have distinct pulses within that 30 million years. It's not a slow, gradual creep necessarily. And so to recognize, instead of kind of the tortoise moving very slowly to have all of these geochemical processes operate, you have pulses that are much, much faster. And that changes the way that you think about systems. It changes the way that you think about geochemical cycling.
Yeah, I love that example. And I'm curious, are there any big common misconceptions or myths about these fields, petrology, volcanology, geochemistry, that you can debunk for us today?
I think one of the big ones is that there is this disconnection between deep earth processes and the hydrosphere, biosphere, and atmosphere. And the big one there is we can't really decouple that from any angle we want to take here. We have to think about the way that rocks are weathering at the surface, the way that magmas are migrating in the subsurface, or even not even magmas, but volatiles are moving through the subsurface, and how that can affect water quality and ultimately the health of populations in those areas. And there's just so much of the focus that seems to fall on this is all a shallow problem. And it absolutely isn't. And if we aren't making those integrations, we're really not focusing on the whole picture.
I love that you mentioned that because I always love talking about the interconnectedness of all the spheres, right? The atmosphere, hydrosphere, biosphere, geosphere. And it's so important because I'll tell my friends about my research, reconstructing past ocean chemistry and how that can help us reconstruct climate. And they're like, but it's ocean chemistry. What does it have to do with the atmosphere? And I'm like, but the atmosphere and the ocean are talking to each other. And it's just this interconnectedness that people don't understand. So you have to have the understanding of how atmospheric chemistry and atmospheric physics work and how that interchanges with the ocean and how the ocean is circulating, how the chemistry of it works. You have to have all these scientists, these different fields communicating to really get one answer, which is just nobody thinks of all that, but it's all interconnected, which I just love.
It is all interconnected. I love it. It's so cool. I think a big misconception that I get from talking to some of my non-geologist colleagues is that we already know everything about how the earth works. When we're still discovering new things all of the time, they just drilled to the mantle for the first time ever, right? We like to talk about, the moon or space is this unexplored frontier, but that's more volume of our planet than any other part of the layers of the earth. And we've only just gotten the tiniest little glimpse of it. We're discovering new mineral phases all the time, and we learn new things about the way that magmas move and evolve. We're not even sure exactly how we made the first ocean ocean crust. There's so much stuff that we can still learn about the earth. And every time that we learn something new, it fits within this larger paradigm that helps us be better citizens of the earth, but also do things like make advances to use more green energy. So it's just like we don't know it all.
I used to be under that exact impression as a student. As an undergrad, you're reading these textbooks and you're listening to your professor, and sometimes they make it sound like this happened, then this happened, and we got here, and now we know everything. And then I feel like once I started actually doing like research and reading papers, once you move from textbook to papers, you realize that there's so much we don't know. Yeah. And every paper ends with like, more research is needed. And it's like, there's just so much opportunity out there to answer more questions and to find more questions we didn't even know we needed to ask, which is just so cool.
Yeah. Every time we don't know something, that's just an opportunity to learn something more and to keep working on it. I think another misconception too, and this one like bugs me sometimes, is that all geologists work in the field all the time, that like you have to be willing to climb mountains or to spend the whole day in the dirt all day, every day, if you want to be any kind of geologist, not even a petrologist. But really, there's a little bit of something for everybody. There's lots of technology that goes on in labs, and we need people who can write excellent code and who can run instruments as well as be in the lab all the time. So I just wish that was less of a misconception broadly across all disciplines of geology, that there's something for everybody. You don't have to sit in the dirt all day if you don't want to.
Yeah, or if you can't,
exactly.
It goes into accessibility too. I mean, there's so many people that might think that they can't do geology because it's a field science and you have to have there are physical demands you have to meet. And that's not the case for every position. I've talked to many geologists now who have various careers in industry and academia, and they just work at a desk, or they just work in the field, or they have some mixture, but you can really kind of tailor it depending on what your abilities or wants are.
Yeah, 100%.
Nikki, do you have any myths?
Well, I don't know about a myth, but I do want to echo what Michelle is saying, is that there's so many different ways that you can be a geologist, and there's different ways that you can be a petrologist. So for instance, if you're not interested in going to the field, I talk to my students there, right? We don't know what's in the deep mantle. We can't go there, right? Even fine, we've just scratched the top, but like we can't get 660 kilometers down. But what we can do is experimental petrology. So if you like baking, right? Like here are your cups of ingredients, and like how do we mix them together, and what temperature do you bake them at for how long, and what do we see, right? So these opportunity to experiment and to create these physical models or to create computational models. And I just want to say to any students or younger people that are out there that are, curious about this, but have this idea of like, well, they kind of have it figured out already. Just keep asking questions. That is the best way. You're going to find out that in intro geology, we're going to introduce you to so many different things. And then if you pull the thread on any of them, you will learn how much more there is to say. Like, we've introduced you to a concept because we have to start somewhere. But as soon as you ask, well, what about that? Usually the answer is, we would really like some more studies. So please get engaged. Come see what the starting point is and start asking those questions.
Oh my gosh, yes. It's like that little kid, instinct of always being like, but why? We lose that at some point. But if you, but why in your geology classes, you'll start to realize there's a lot of things we still have to learn. So what do you hope participants take away from this technical session that you're going to have at GSA?
I think this conversation is really indicative of kind of what I'm looking forward to at this session. Is it's really hard to be optimistic and happy about our science right now. And we're all just so passionate about what we do, why it matters, and why it should matter to other people. So I think it'll be really wonderful to kind of bring a group of people together and have those conversations and see people be passionate. See if we can bring in some discussion blocks between talks and things like that to where we can spark these new ideas and kind of avoid the doom cycle for a few hours.
Absolutely. That is so needed right now. It'll be really nice at all the sessions, but, especially those that, you're getting these like-minded people together and all coming together to talk about the importance of these things and the importance of why they should be funded and all these things. I mean, that's going to be so, hopefully, so, reinvigorating to these researchers that we're all in a state of kind of like feeling undervalued. So I think that'll really help to motivate and kind of reinvigorate the morale we need to go forward and come up with new ideas and things, which is so exciting. And on these kind of new ideas and, major outstanding questions that are in these fields of petrology, volcanology, and geochemistry, what are some of like the biggest unanswered questions that still need to be answered? And how can students maybe get involved in the research that helps answer these questions?
I would say that one of the conversations that I've been having with igneous petrologists that are particularly interested in magmatic systems is how do we redefine the intro textbook image of like a big balloon magma chamber at depth? We know now that that's not real, that that's not how these systems operate. And so one of the things that I'm really excited to see how they develop is how do we redefine this sort of cartoon image into something that's more realistic? How is melt actually transiting the crust? And how is it chemically evolving as it does so?
I think on top of that are all questions of magma storage, like how long it sits under the ground before it erupts. What are the qualities of magma necessary for an eruption to happen? Like people want to talk about that all the time with super volcano eruptions. Everyone's very concerned about Yellowstone all the time. So, I think there's a lot there. I also think about volatile cycling a lot. We haven't talked about, we talked about fluids, but like the volatile cycle, a lot of volatiles are why we are able to live on this earth, and there is an inherent connection between the atmosphere and the surface and the critical zone and the deep earth, and we don't understand at depth how volatiles are recycled, how they're stored, how they move from one reservoir in the earth to another, but they're incredibly important for everything that's living on the planet. I think the second part of your question was how students can get involved. Everyone who's going to be at GSA has a curious mind. Literally everyone. They're only there because they're curious about things, and they have ideas and want to be working on research and in the future. And so if students are present at GSA, or even if they don't get to come to GSA, go talk to your professor. Go talk to your professor and tell them the things that you're interested in. Honestly, when we get to talk to students who are passionate or excited or really just interested in something, that makes me excited and interested in something too. And I think that's a quality like professor wide. That's the best way, is to ask questions, go talk to somebody, get involved. Ask what research opportunities are available at your school. And if there is not something available at your school, look into summer programming, email other professors. Most of us will move mountains to make it so that people get to work on a project that they're really interested and excited in.
It's so true. I have had multiple internships and opportunities to work on research just from emailing somebody. There was no position that I applied for. I just emailed a professor or PI and said, this is cool research that you do. Can I come work on it with you? And they had extra funding for a student, and I did. So it's so important just to put yourself out there. It's scary, but it'll so be worth it. And it's like, there doesn't have to be an official position. Just go talk to people, or maybe they will point you in the direction of an official thing, but sometimes they'll just, move those mountains for you. So absolutely. I think this conversation has been really amazing and eye-opening for me. And I think it will be for a lot of people as to all of the ways that these fields do impact society and just our daily lives directly. I mean, everything that I'm currently filming on comes from Earth, but you don't make that connection, and making that is really just important for kind of opening your eyes to everything that we need to have a future. But yeah, I think this has been really insightful. So thank you so much for coming on. And yeah, I will put, for those listening or watching, I will put everything, all the links down below if you're interested in attending GSA. And yeah, with that, thank you again.
Yeah, thank you. Thanks for featuring sessions. And I really hope that this session gives people ideas and passion for the future.